I think we made the case before with why we're interested in pipe flows. It's not necessarily that we're interested in making you into HVAC engineers to design people's plumbing systems in houses. But certainly within this country, you see it here. We talked before about this capillary distribution of natural gas pipelines, basically taking stuff formerly from the Gulf to the Northeast, where all the population lives, and now you see this network in Pennsylvania also. And so we mentioned last time, but perhaps we didn't really show it in any detail, the fact that up in the Northeast, in Pennsylvania, northwestern Pennsylvania, there are certain places where this stuff is stored underground. The Strategic Petroleum Reserve is I don't know how many billion barrels of oil that is held in reserve in case there's another mid-1970s type embargo of oil, which of course isn't so important these days because the US or North America is basically energy independent or oil independent, largely because of the tar sands in Western Canada, which have more bitumen than Saudi Arabia in them. It's just this very, very heavy oil. And so the Strategic Petroleum Reserve is typically in salt, underground. It's not sitting above ground or at gas stations. It's sitting a few thousand feet down in salt. And likewise, in the north and western part of Pennsylvania, the same exists. I don't know, I didn't look at this any further. But the basic idea we mentioned last time, you drill a hole, you case that hole with a steel casing, and then you circulate water at the bottom of that hole up into an annulus above the casing. You slowly retract the casing, and you dissolve out a hole that looks like a cigar, a big cigar. Cigar may be 100 feet in diameter, maybe 1,000 feet tall, like a cigar. And it is able to take natural gas in it, bless you. And when you want to recover that natural gas, you have a brine pool on the top. You just pump the brine in, displaces the gas, and you send it off on part of this prior network across the country to be able to be where it needs to be. And so having this up close to the consumption centers means that it's easy to get it to New York City when everyone turns their stuff on. Yeah.
Is like an oil pipeline and a natural gas pipeline, are they kind of the same, or are they totally different?
I think, well, it's not my area, but I think they're just sealed pipelines that are able to take fluids.
Okay.
And so
Like, does one have to be like, I mean, natural gas probably has to be pressurized, so it has to take more pressure.
but I think the natural gas would also be I don't know whether it'd be thinner or not, because it would need to take more pressure, but I don't think the pressures are very high. The higher the pressures are, I guess, the more efficient the production is. Actually, if you look at maybe it was the exam last year, the third exam, there was a question. Of course, it won't repeat, so it doesn't help you. But there was a question basically looking at the energy density of natural gas as it's sent, and the energy costs that you have to provide to send it 3,000 kilometers. And so it turns out that the energy density is very high compared to the energy costs, which is obviously what you want, but they wouldn't necessarily stop us. Of course, one of the dilemmas of renewables is if you want to be able to fuel things like airplanes, the ways that airplanes work is that they have this incredibly high energy density fuel, which is jet fuel or gasoline, as a liquid at room temperature, which is tough to emulate. Certainly you can't do it with natural gas, right? If you want to do it with natural gas, you have to have a pressurized container to be able to contain it on your car or whatever, on your plane, which you can't afford to do. And then because only at very high pressures and at relatively low temperatures can you reduce it to a liquid which has similar energy densities to that of gasoline. So gasoline just happens to be this wonder fluid. Gasoline and jet fuel happen to be these wonder fuels. And so when you look at before the shale gas boom, all of Australia's wealth came from drilling gas off the northwest shelf and then liquefying it, cooling it down minus 100 centigrade, 150 centigrade, so that you could transport it to Japan and China, which were the main consumers at that time. And that still exists, but and now the ports that were thought to be needed in the US maybe 10 years ago, when there were plans to build liquefied natural gas terminals to accept imports, are no longer needed. They were planned but never built. And now the question is whether you produce them and actually use them for export, so that you can take natural gas, which sells for $3 a thousand cubic feet in the U.S., and sell it to Europe, which is hamstrung by getting gas from Russia, which could change in an instant, and you can sell it probably at double the price in Europe. And so interesting perspectives, I guess, on the whole energy picture. We looked at San Bruno. We didn't talk about this. Earthquake regions, one of the big problems in earthquake regions, if you have an earthquake, then you breach pipelines then explode, and you have problems from that, obviously. And so certainly in place is this idea. We talked about it for tsunamis, right? If you have a tsunami 100 kilometers offshore, you have ocean bottom seismometers. You know when the earthquake occurs. It takes you 20 minutes to get the tsunami, and so you have some warning system able to do that. The actual wave traveling 100 kilometers onshore takes something like a couple of minutes to get to Tokyo. And so also you can have an early warning so people can leave buildings or do whatever they need to do before any shaking occurs. So you can do the same with having automatic shutoffs for the utility system. Water would be included, but obviously natural gas being supplied to people's homes is a much more volatile component. And so having earthquake shutoff valves is something that's a reality these days. We looked also at this water explosion into a gallery. Again, we don't necessarily think of it as a piping system, but hydroelectric plants, upstream reservoir, downstream generating plant are joined by some pipe. Happens to be a pipe that is probably 3 or 4 meters in diameter, 10 or 15 feet in diameter, typically lined with steel close to the transformer locations, so it doesn't jack open the mountain and bleed off and hydraulically fracture basically the mountain and destroy the pump house. And sometimes that goes wrong with not closing a gate or doing whatever it was in this Russian example that we looked at before. And we can look at it again because it'll just take 2 seconds. Yeah, the night shift, and then unfortunately, whatever goes down. So, yeah. So we looked at that before. So anyway, so again, making the point of the solemn responsibility of engineers for the public interest, and scientists as well, but engineers especially. And I guess maybe something not quite so exciting, but dealing with effluence from people's houses, not influence such as natural gas, but effluence from people's houses is looking at, I'm not sure why we're looking at this, but it's a system for sewage control, I guess. So, and again, linked up with a piping network to be able to move things around with solids in the piping, of course. So, not what we need on a Wednesday morning. Okay. All right. So, let's forge ahead. Let's see if this is going to cooperate today. As I mentioned earlier, there was physically nothing wrong with it before. It worked when I tried it yesterday as well with the projector. And so let's see if we're lucky today. Where are we? We should be at 11.2, but let's recap. Yeah, okay. Let's get rid of this. Let's get this. And let's do this. And let me make it a little larger. Okay. All right. Okay. If you looked at 11.1, you'd have seen these. Well, let's. Let me just pull this out for a second so I can see what it does when it's not linked. No, it doesn't like doing it even when it's not linked, so that's interesting. This is recap. So is that up on this? So basic recap is only this. So I guess it'll slow me down. So we had a Moody chart that you will recall, and it's divided into 3 regions. And the significant lines that we have on there are something like this, something like this, and some lines like this. And these are epsilon over diameter, large. Yeah, apologize for this. Epsilon over diameter, small. This is epsilon over diameter equals 0. In other words, absolutely smooth. This is 2000. This is 4000. This is Reynolds number, where the characteristic dimension of length is diameter. Velocity, diameter, density over viscosity. Today we'll also talk about this in terms of velocity, diameter, and kinematic viscosity, which we'll call mu, which is just the ratio of dynamic viscosity. So mu is just equal to the dynamic viscosity divided by density. Turns out to be a convenient way of thinking about viscosities, different units of course. And what are the take-home messages? The take-home messages are that in this zone here, this friction factor, which I didn't label, and we know that by definition friction factor multiplied by length over diameter multiplied by this velocity term, velocity squared over 2g term, in the pipe, not the fitting, not at the nozzle rather, gives us this value of loss coefficient. And it's a function of 2 properties. One is roughness and diameter, and one is Reynolds number in the laminar regime, and it's also a function of the same properties in the other regime, or potentially a function of the same properties in the other regime. Again, apologies for this. But we know that here it doesn't change with Reynolds number because it's absolutely flat, and so in the turbulent regime it's not a function of Reynolds number. In the laminar regime we only have a single curve for any particular pipe, and so it doesn't change with the relative roughness, and so this term doesn't need to exist. So in the laminar regime it's only a function of Reynolds number. In the turbulent regime it's only a function of roughness. So that's important. And we know that in here this is typically, in the laminar regime, some constant divided by Reynolds number. And that constant was 96 for us for a smooth pipe. If you looked at the materials that we didn't go through in class but we talked about on the video, then you'd have found out that we can look at laminar flow in different shaped tubes, some of which are circular tubes that have an interior insert, and we can still solve these problems if we do 2 transformations. One is that we use a hydraulic diameter as our equivalent diameter, which is just 4 times the area. So the area would be the area of flow that's around the outside here. Sorry, it's the cross-sectional area of flow that flow is going against, and the perimeter would be the length divided by here. So for a regular pipe that would look like this, they would have some diameter d, then the area is just going to be equal to pi d squared upon 4. The perimeter is going to be equal to pi d, uppercase P. And if you take the ratio of these two and multiply it by 4, then you end up that the hydraulic radius would be what? It's going to be 4 times pi d squared upon 4 times pi d. Lose the 4's, lose the pi's, lose one of the d's. I guess it's hydraulic diameter, isn't it? Not radius. And so it turns out to return the value that we have for a circular pipe, just as diameter. But for pipes with non-circular sections, it gives us some equivalent hydraulic diameter. And so we can use that hydraulic diameter in Reynolds number, if we have a non-circular pipe. And we can also use that equivalent hydraulic diameter in this relative roughness parameter, and use everything else the same that we've used before. If you look at the examples that we have for this, just very quickly, that if you have a pipe with an annulus in it, presumably as this annulus goes to 0, this inner component D1 goes to 0, then it must go to 64, right? Because that's the value that we have on the Moody chart. And you see it kind of going that way. This gets to 71.8, but no smaller than that when this is equal to a very small number. But it would go to 64 for 0. Likewise, for a pipe that would have a flat on it, as this alpha values goes to 0, then again it should replicate the values we know. What else? Yeah, okay. That's yeah, there was one other thing that I was going to... Yeah, I guess the other one to mention is that for a parallel-sided duct that has flow going through it, so in other words, if this is a square section duct, if you can see that, 2 parallel sides, then the value of C over RE is actually this, 96. So we have 64 for circular section 1. In this particular case, this is actually 96. So it's a standard result. I think in the previous videos we've talked about using a parallel-sided duct because it looks like a fracture in rock. Fractures in rocks are the same as hydrofractures in rocks, and the fluid transmission along a hydrofracture is controlled by basically a geometry, a duct-like geometry like this, right? If you imagine this just going much longer out here, so it's a blade that comes out of a well, then flow within this blade is basically flow within a duct that you'd have in a house, where B is very large compared to A, and as B over A goes to infinity, or A over B goes to 0, then you can actually get the laminar behavior along that. It probably is laminar. May or may not be laminar in the subsurface. Probably is. Then the value for this is 96. Anyway, spent more on that than I wanted to. Anyway. So also, so that kind of rounds out our Moody charts. If we go back to this, and so those are, I think, there are things you need to know about using the Moody charts. Laminar behavior conforms to something like this, is a function of Reynolds number, but not a function of roughness. Turbulent flow is not a function of Reynolds number and is a function of roughness. And so the solution methods that we end up with tend to be slightly different because we need to know what the flow rate is to know the Reynolds number. So in some cases, we have to go through iterative solutions to be able to do it. Always we'll use Bernoulli's equation. I won't write the terms, but these are the upstream terms plus pump head. And I don't know how to solve this problem of this pen not working. The downstream terms will be written plus the individual components for some of the major losses, J, so perhaps you can see the J, and plus the sum of the minor losses, which are the pipe fitting losses, minor, and this is downstream, if you can make that out. This is upstream. Talk about bringing it to a crawl. Right? And so these are Z plus P over gamma plus V squared over 2G at the upstream point, at the downstream point, pump head that's added into the system, and the losses. Losses due to the Moody chart, and losses here, as you know, are due to pipe losses, which are just a discrete number multiplied by the velocity in the fitting. Okay? So all of our calculations will involve something like that. Because of this difference between the fact that in this regime here, the laminar regime, it's a function Reynolds number, typically the solution methods are divided into three types. The easiest ones are where you want to calculate what the head loss is, and you know what the flow rate is, or you're told what the flow rate is. So in other words, we want to get 1 million barrels of oil out of the pipeline per day at this end, and therefore divide that by the cross-sectional area, and that gives you the velocity that you have in the pipe. And you want to calculate what kind of head loss or what kind of pump you have to apply to be able to move it to do that. This is easy because the velocity is defined in this particular case, and we can solve directly for the friction factor because we know what that velocity is, and we can use that to calculate this. Those are the easiest kinds, so-called type 1 problems. The problems that are less easy are ones where we don't know what the velocity is, and we need to solve for it in so-called either type 2 or type 3 problems, and we'll go through each of them in turn. The type 1 problem, I guess if you looked at the materials online last time, you'd have seen that. So in other words, where you have a flow rate, you can merely solve for all the other components. So I won't go through that again, but that definitely is the most straightforward. Again, it just uses this Bernoulli formula that we're dealing with that we've mentioned. And so what we'll do today is we'll do a couple of cases where we need to actually solve for the flow rates or solve for the geometry. So we want to get 1 million barrels of oil out. We'd like to know what kind of size pipeline we need to be able to do that, and therefore, again, we don't know the velocity. We don't really know explicitly the velocity because we don't know the size of the pipeline, and so we can't calculate the velocity without the size of the pipeline, the cross-sectional area of the pipeline. So that's what we will attempt. So let's see how far we get with that. Okay. So I will go through in kind of overview. I don't want to solve them piece by piece, but it'll be worthwhile just talking about the rationale of it, right? So here's an example. So there's a pipeline that goes into the page. It has a T that comes off it, off the pipeline, but it also has a vertical closed chamber coming off it and a spigot that can be closed. And so actually this is a bit like a hydroelectric dam. If you think about this, instead of being horizontal, being inclined, upstream lake, downstream effluent from the turbines, then typical hydroelectric plants not only have a tunnel coming down, but they have a surge, what's called a surge shaft, which is a vertical shaft filled either open to the surface or just filled with air, so that when you close the valves off down in the generator hole, and you do it in a hurry, that all the momentum of this water coming downhill, which has a lot of momentum, mass times velocity coming down, that you want to shut off just like that, instead of hitting the gates and blowing the gates out and kicking them into the turbines themselves, it actually has somewhere to go by taking the momentum and pushing it up this surge chamber. So it happens to be something that's in a piece of fabricated pipe, but it also exists in other systems also. And for the same reason. So that when you shut this valve off here, the water that's charging down here, or the fuel oil that's charging down here, instead of busting this valve off, it actually has somewhere to dissipate its energy into the system. And so the question is that initially, when this is closed, by definition, if you did Bernoulli between these points with velocities 0 throughout the system, you'd find out that the pressure through this would have to be the same all the way through, because they're the same elevation, and you could do that. And the question is, with it closed, it has a certain amount of height within this chamber. When the valve is opened and the pressure changes at this location here, it would be high here at the original pressure, and it would be low here because it would go out at atmospheric. So initially, the pressure distribution along here, if we looked at it, it might look like it'd be roughly linear. Would be the initial pressure versus location. And the question, no, sorry, once it's open. Initially, once it's closed, it would have to be this. And you could confirm that by just using Bernoulli to make that case where these have the same elevations. All the velocities within the pipe are 0, so the only term you have is P1 over gamma, P2 over gamma. You know P1 over gamma here, and P2 has to be the same at all these other locations. So that's this case here. This is the first case. And at that, with 400 kilopascals acting here, we have a certain height of this fluid column within the surge chamber. And so if I just read through the question, when it's initially 400 kPa and a closed valve, then the height is 0.4. So this H is equal to 0.4. And then once you open this valve, what's going to happen? Well, the pressure is going to drop. It's going to drop to atmospheric at 2, and it's going to do something in between that. We don't know what this value is. But we're going to have a new pressure acting at 0.3, which won't be 400 kPa anymore. And it must go down. And if it goes down, then the height of the column, the water that's in there, must also expand because it's having less pressure applied to it. So that's the essence of the problem. So the question then is to be able to solve the system of equations by figuring out, first of all, what the pressure is at 0.3. So we open it up. If we look at 0.3, we don't know the pressure. We don't know the velocity. That's a problem. There's two things we don't know. If we know this, we know the pressure is 400 kPa. We know it's a big pipeline, quote unquote, so we can put the velocity 1 is equal to 0. When this is open, we know this is atmospheric. We know the elevation, which is the same as this, but we don't know the velocity. So in other words, we could solve for velocity 2, because we know everything else. If we know the velocity 2 here, then by continuity, we know the velocity at 0.3. And so then when we write Bernoulli a second time, we know a velocity, we know the elevation, we don't know a pressure, I'd like to know it, and we know all the other things at some other location. We either know all the pressures, velocities, and elevations here, or we know all the pressures, velocities, and elevations here. Right? So this is Bernoulli, written for this, as you've seen before. Upstream, downstream, head loss in the pipe, head loss in the fitting. 2 fittings, I guess. And so what do we know in this? We know this pressure. We know there's no velocity. We know that the elevations are the same. We know that this should be atmospheric, right, if it's 2. We know that the velocity at 0.2 is whatever it's coming out of this valve at. And since we don't think we're not given any information about any different value of the orifice size versus the pipe, then you can assume they're the same, which is useful, which means that you can assume that V2 is exactly the same as v. Right? So note well that this is v, right? Not v2. It's the velocity within the pipe and the velocity within the individual fittings. So we're left with a pressure to calculate. Oh, sorry, pressure that we have. We don't know what the velocities are, and so we just need to know what these coefficients are. We know that the friction factor is 0.2, so I guess by definition that would imply that the flow is turbulent within it. If we take the implications of our Moody chart to be able to explore that, right? If this friction factor is constant, it means that we're somewhere over here, and so it means that we're in the turbulent regime. It doesn't really matter for this calculation, but that would be the implication. And we take the length of the pipe, which is 13 meters, length over diameter, friction factor. This term here is here. This term here is this one here. And if we go back to look up our values for different fittings, this is probably for a T, and this is for a spigot. You remember these charts, tables, it's not important what they are, it's just pulling a number out of here. And I'm guessing that valves, angle valve fully open or a swing check valve, I don't know. This would be one of them. A T with fluid flowing in it would be this one. This is the 0.9. So the fact that it's flowing through here only, it's not going up here. This is just this surge chamber, which only gets activated if you shut the spigot off the valve, and then it will go up there. But you need to use the appropriate numbers for that. You never knew pipe flow could be so exciting, did you? So these are these. And so the only unknown that you have now is the velocity. And solve for the velocity. That's the velocity at 0.2. Once we know that, we could write Bernoulli between 0.1 and 3, or between 2 and 3. It doesn't matter. In this case, it's written between 1 to 3. We know the velocity here is 0. We know the pressure is 400 kPa. We know the elevation is 0. We know that the pressure here we don't know. We know the velocity has to be the same as this velocity we've just calculated here. And we know the elevation. And so we could use Bernoulli again with these lost terms. This again is the velocity within the pipe. And the only thing we can solve, we solve again for this, we can solve for the value of P3. So without belaboring it, we can use the information to solve for P3. So now what we have is we have the pressure at this point P3, this is 0.3. We know what it is when the valve's closed, which is 400 kPa. We know what it is when it's open. We'd expect that it would be less than 400 kPa. In fact, it is. It's 187 kPa. And so what we can do is we can use that to be able to draw this picture in two cases. We can draw the surge shaft in case 1. And in case 1, the pressure is 400 kPa. And we know that the height of this, when that is the case, is equal to 0.4 meters. And we know an area of this. And we know the total height is equal to ½ meter, which I won't write on there because I can't. So this is 0.5. Terrible. The other case we know is when it has a different pressure acting on it. And that different pressure is 187 kPa. And we would presume that with the lower pressure now, that this value H is now different. And that therefore this value here is larger because it's expanded. So the only thing we know about this is that this volume, this mass of air that's in here, or whatever the gas is, has to be the same mass. And so we can write the fact that this product of density, so in other words, density times volume is constant. And so if we can write this in terms of the density in terms of the ideal gas law, which is what this will conform to, we can write density in terms of a pressure. So density is equal to a pressure divided by RT. If we assume that RT is constant because it's one gas and it's the same temperature, then we know that density is equal to pressure times some constant. So we can substitute in this, and basically we know that the product of these two has to be constant. And so all we have now is that we have the ideal gas law to define the density, and we have the volume, which is going to be area times 0.5 minus h, right? The volume of this volume here, is equal to what? 0.5, that's best I can do for 5. Oh. Minus h multiplied by a. And if we can use the manometry equations to convert the pressure here, what is the pressure here relative to this pressure at this point? It's going to be 187 kilopascals minus h times the unit weight of the fluid. And so we can change the pressure to be able to get that magnitude. And so basically it's just a game to be able to accommodate those two components. One, the fact that the mass of air in here has to be the same, and so this holds. We can define the volume as a function of this height multiplied through by cross-sectional area. We can define the density as a function of pressure, and we can define the pressure at this point as a function of the applied pressure here minus a unit weight times the height above it to get each of these things here. And so if we end up solving for that, it gets a little bit complicated, but that's basically the solution that's used. So more complicated than it needs to be, but at least makes a case. Actually, it's a real world problem. I think these surge towers actually physically do exist in commercial and residential piping to be able to stop knocking within pipe networks, to be able to absorb the shocks of shutting valves. Okay, more complicated than it needed to be, but anyway. So a second one, another pipe type 2 problem. So flowing out of a tank, we get a prescribed flow rate of a given magnitude, which is given. Determine the flow rate expected if the pump is removed from the system, if the pump is adding initially 25 kilowatts to the system. So in other words, initially it's pumping, it gives a flow rate of 0.4 meters cubed per second when it's pumping at 25 kilowatts. When you shut it off, we want to know what the flow is as a result of that. So I guess to do that, we need to be able to figure out exactly what the situation of the pipe system is in the first place. So we can write Bernoulli between upstream to downstream. In this particular case, the nozzle has a different diameter from the pipe, and so that's worthwhile noting. It must be turbulent also because you're given a friction factor to be able to speed your calculations instead of iterating. And if you write Bernoulli between upstream and downstream, you have these terms here. Pressure upstream is what? Has to be 0, right? Velocity upstream, big tank. Get rid of both of those. Elevation, we don't know, which is the unknown in the first part. But we know it's flowing, so we don't know what Z1 is. We know that this is the equivalent of 25 kilowatts, but it's a pump head, not kilowatts. Pressure 2 has to be what? Atmospheric. Elevation 2 is 0 if we take this as the datum, which we have. We don't know what V2 is, but we know what the flow rate is. So I guess we'd know that V2 times A2 has to equal Q2, Q. And we'd know that V pipe, A pipe, also equals Q. And so this term here we would know just from the flow rate. This term here is a different magnitude, but we'd know from the flow rate. And so I think we have everything here we need to solve for except for H. Right. So we know that the pump head is 25 kilowatts. We know that we can define pump head as a function of, well, what is pump head? Is equal to kilowatts or watts divided by, if we write it in flow rate, it is the unit weight of the fluid multiplied by volumetric flow rate. So in other words, you have Q, Q, and Q here. They're all the same Qs. And so we can calculate what HP is. So we know what that is. And so, sorry, this one. And so the only unknown we have in this whole equation, we know the friction factor. We know the length of pipe is 30 meters long and a diameter of 60 millimeters. So we know absolutely everything here except for green H. Solve for green H, it turns out to be 133.2 meters. So now we know that that is the geometry. And so now if you take the pump out and solve it, you can just write Bernoulli's equation again between 1 and 2. We want to be able to solve for the flow rate through the system, which we don't know. And if we do that, this is what we do. So without the pump, HP, it'll just look exactly the same expression as this. We would have, okay, what did I do? So, yeah, okay, that's not true, right? Once you calculate the head of water in this, it's actually 69.5 meters. So this is 69.5 meters. I misspoke. So we have that number. So once we take the pump out, we can write again the behavior between upstream behavior, elevation, pressure is 0, velocity is 0. So the only term on the left-hand side is elevation. The pump head is 0 because it's been taken out. So this is the upstream portion. The downstream portion will be a velocity here, a pressure here which is 0, an elevation which is 0, which is this term here. And we'll also have the losses within the pipe which exist here. And so again, we know that these still are true. Relative velocities within the pipe and within the fitting. And we can relate those by conservation laws to be able to figure out exactly what the magnitude is of the only remaining variable. And the only remaining variable is velocity that we want to solve for. That's it. Okay. So iteration here. All of these problems are made much easier by the fact that we assume, or that they're assumed that they're turbulent, and you get a single value of friction factor for it. Because you don't have to go back to the Moody chart to be able to figure out exactly what's going on. All right? Yes?
Which is thus H plus HP equals what is H that it's V squared over 2G?
Direct me where I need to be.
It says thus.
Thus?
Higher.
This previous thus. All this, yes, okay. So this is basically writing out Bernoulli's equation, including the head on the left-hand side, which is Z1, the pump head, which is, we know because of the flow rate, and this term here would be the first, this would be this velocity here. Is that what you're asking?
Yeah, I just don't understand why is. Okay. So
This is 2 times acceleration due to gravity,
Okay.
and this is v squared. So it's this term here. This term is going to be the friction factor. This is L over D. And this is the other v squared. This is v squared over 2g. So I can write that. And this one is v2 squared over 2g. Okay? Is that the question? Yeah, okay. So it's, the rest is algebra. Again, well, we're right, we have 2 minutes to go, so I'm not sure we have time to necessarily do this. But again, it's writing, and so also keep this in mind for your midterm, between writing Bernoulli's equations between two locations, upstream and downstream. Here's upstream flowing out. If you have losses in the system, upstream has to be the one that's flowing from, downstream has to be the one that's flowing to. Otherwise, the heads for the losses and for the pumping don't work out. So always remember that. And this is again writing Bernoulli between this, upstream, not atmospheric because there's a head of water here, right? This has to be the pressure here because you can get to this point from this location. So the pressure at this point has to be 8 feet of head. So this magnitude has to be 8 feet. Big tank, velocity 0. Depends where you take your datum. If you take your datum here, then this is 5. There's a pump in there. P2, squirting out at atmospheric, by definition 0. Velocity, we don't know. And again, this would be the velocity within the pipe. If the pipe and the nozzle are the same diameter, then they have to be the same velocities, which makes life easier. Length over diameter of the pipe you have here, and friction factor probably you have somewhere. Friction's constant. Do I see it? No, that's it. What else do you know in this particular case? Friction factor is constant diameter pipe. Oh yeah, this is the friction factor. So you have a friction factor, minor losses are negligible. Don't care about the bend, that's what the code for that is. Minor losses are negligible, is code for the fact we don't care about that bend. Determine the flow rate if the pump adds 1 horsepower. Oh, we're in trouble here, this is in English units. But if we know what the pump head is, if we know what the horsepower is, we know immediately what the pump head is. The only unknown is v squared, and we solve for v squared in the system. It turns out that this works out well because the pressure here, which is equal to this elevation here, and the elevation of the outlet are both equal to each other. If, for instance, you raise this outlet by some small amount, by 2 feet I think in this question, then all of a sudden you get a horribly complex solution, because all of a sudden the elevation of this pressure term here and the elevation of this Z2 term here, in this particular case the 8 feet here and the 8 feet here exactly cancel out. If you don't have them cancelling out, that you have a remnant, you have an extra term on the left hand side, and instead of getting a relatively simple expression, which is this one here, I'll let you look at it on your own, because you only have a quadratic to solve. All of a sudden you end up with a cubic term, and you end up with a much more complicated, a much more complicated solution. But it's the same solution, but it's just writing Bernoulli between upstream and downstream. And so they just vary slightly differently. And maybe we'll spend some time doing this next time. So the third type of problem, we spend our time doing the second type of problems where we don't necessarily know what the velocity is within the system. If we want to be able to dimension a pipe to be able to carry a certain volume, then we actually have to iterate using the Moody charts for many of the systems that we need to deal with. And so that's important enough that we'll save that for next time. And next time also, on Friday, we'll kill off flow with looking at networks of pipes. Not just single pipes, but when we have networks in parallel or networks in series, and the solutions directly follow exactly from what we're dealing with here. All right, thanks very much. Enjoy the day.